Good morning. So in this lecture I'll make some relationship between electric field and electric potential. So in my previous lecture I discussed what is electric field and how to calculate the electric field for point charge infinite where with charge density lambda coulomb per meter, and what will be the electric field at a distance r, and also calculate the electric field for a infinite metallic sheet with uniformly charged densities sigma coulomb per meter square, and I'll get that result equals to sigma by twice epsilon naught, and it is independent of height. So in this lecture I'll discuss what is actually electric potential and how electric field and electric potential relate with each other. So now if I'll consider, suppose there is a plus charge q over there and another charge small q placed at infinity. Now if this charge q moving along this direction, initially assume this is infinite. So when the distance between plus q to this charge q, the distance is x, so then the force acting between these two charge particle, that force F equals to, according to Coulomb's law, the force F equals to 1 by 4 pi epsilon naught capital Q small q by x square. Now next, if I'll assume this small charge q moving by a small distance dx along this direction, that is dx, then the work done dw, the work done equals to f dot dx. See, in this problem, if capital Q and small q are similar in nature, so that time the force will be acting outward direction because there is a repulsive force, and the displacement is inward direction. So obviously the angle between force vector and the displacement vector equals to 180 degree. So that's why I can write that is f into dx into cos 180 degree. So the value will be minus, cos 180 degree is minus the value of force equals to 1 by 4 pi epsilon naught capital Q small q by x square into dx. That is dw. So the total work done equals to minus capital Q small q by 4 pi epsilon naught integration of dx by x square. Now if I imagine finally over here the charge will be placed, and that time the distance between capital Q to that charge equals to small r. So initial point is infinite and final point is r, so that's why limit will be infinity to r, and the result will be minus capital Q small q by 4 pi epsilon naught integration of dx by x square will be minus 1 by x infinity to r. So this minus getting plus, and I'll get qq by 4 pi epsilon naught into 1 by r minus 1 by infinity, and finally I'll get the net work done equals to capital Q small q by 4 pi epsilon naught into 1 by r. The definition of electric potential is that amount of work done required to bring a positive charge from infinity to a particular point r is called the potential. So what is the potential? Potential equals to work done per unity charge, that is W by Q, and the result is 1 by 4 pi epsilon naught Q by R. So if I multiply with the charge small q, I'll get the total work done. Okay, and this work done will be stored as a potential energy of the system. So basically both are positive charge, so the q always feel the repulsive force outward direction. So you have to do some external work done, and this external work done basically stored as a potential energy of the system. That's why the total work done W equals to Q into V. Okay, so for any kind of electrical problem, if there is a lots of charge over there, and if I'll bring a charge, another charge at any particular point, so if I able to calculate the electric potential at that point and multiply with the charge, then I'll get the stored potential energy inside the system. Okay, now if I recall the previous concept of electric field, suppose there is a charge q, and at a distance r, suppose this distance is r, at a point a, suppose there is a small charge q. So initially I can assume for this q charge at a distance a, the potential at that point equals to V. So I can write the potential at point A equals to V. I can write VA, the potential at point A is V. And if the charge is placed by a small distance, that I can write, that is dr. So at that point obviously the potential will be increased, because if you go very closer to the charge q, the potential basically increase. So close to the point, if I give the name the point B, I'll assume the potential is V plus dV. So I can write the potential at point V equals to V plus dV. Now if I'll calculate what is the work done to bring the charge q from point A to point B, the work done is nothing but the change in potential. So what is the change in potential? VB minus VA multiply with the charge q, which basically move from point A to B. And already I know the potential at point B equals to V plus dV minus V into Q. So the net work done equals to Q into dV. Now if I recall the very basic concept of work done, so what we know actually work done? Work done equals to force into displacement. So basically F dot dr. Now when the charge particle move along this direction, but the force basically acting in opposite direction, because when charge are same, so there will be some electrostatic repulsive force. So obviously the angle between force and displacement equals to 180 degree. So I can write that is mod of F into mod of dr into cos 180 degree, and that is nothing but minus F into dr. And what is actually force? Force is nothing but charge time electric field at that point. So I can write instead of F, that is minus Q into E into dr. So here I'll apply the concept how to calculate the work done by the difference in potential between the 2 points, and here I'll use the very basic concept of work done. Now if I'll compare these two equations, finally I'll get that is Q into dV equals to minus Q into E dot dr, and finally I'll get E equals to minus dV by dr. Okay, now what is actually dr? Dr is the displacement, and when we are talking about displacement, so if I'll consider initially it is a Cartesian coordinate system, so that time I can write in Cartesian coordinate system that dr, the displacement, is nothing but equals to dx along I plus dy along j plus dz along k. So I can write electric field E equals to, in Cartesian coordinate system, that is nothing but del V by del x plus del V by del x along I plus del V by del y along j plus del v by del z along k. And here the operator del x along I plus del x del y along j plus del z along k is called the gradient operator. Basically, gradient operator find what is the change along x, along y, and along z. Okay, but instead of Cartesian, if I'll consider a cylindrical coordinate system, then there will be change into the gradient operator, because in cylindrical coordinate system, if I'll consider the parameter are r, theta, and z, so that time the gradient operator will be del of r along r direction plus 1 by r del of theta along theta direction plus del of z along z direction. Why? Because in cylindrical coordinate system, when I write the length vector dl, I can represent the change along radial direction, that is dr, along r direction. But if I make a small change along theta direction, actual the change in length equals to r d theta along theta direction, and the change along z is dz along z direction. So pictorially, if I try to represent this phenomena, suppose this is a cylinder, and inside the cylinder, if I try to move from this point to that point with an angle, variation of the angle is theta, but actual the change of the length equals to r into d theta. Okay, that's why this is 1 by r. Similarly, instead of a cylindrical coordinate system, well, we consider a spherical coordinate system. So that time the length vector dl, I can write dr along r direction plus the parameters are r, theta, and phi, that is r d theta along theta direction plus r sin theta into d phi along phi direction. Why? If I'll consider this is a cylinder, if I'll move r direction, the change in length along r direction is dr. But suppose if I'll move from a point to b point, and if this angle is, this is a, this is b, if this angle is d theta, so the change in length equals to, this change in length equals to r into d theta. Now if I move along this direction, so that time the radius is not r. Basically it is moving with the radius. If I'll consider this is theta, so this is r, and r, this radius is r sin theta, and within r sin theta radius I'll moving an angle d phi. So this length basically r sin theta, this length basically r sin theta into d phi. So when I'll consider a spherical coordinate system, that time gradient operator basically change, and that time the gradient operator will be del of r along r direction plus 1 by r del of theta along theta direction plus 1 by r sin theta into del of phi along phi direction. Okay, so in Cartesian system, initially it's look easy, but actually to solve the numerical problem and the problem regarding your field theory, the cylindrical coordinate system is much more easier. Initially it's look little bit difficult, but if you understand, if there is a change in theta, what is the change in length? The change in length equals to r d theta. If their angle is change is d phi, actual the change in length equals to r sine theta into d phi. So if I write what is the gradient of potential in Cartesian coordinate system, so that is basically del v by del x along I direction plus del v by del y along j direction plus del v by del z along k direction. If I write in cylindrical coordinate system, so the only change is del v by del r along r direction plus 1 by r del v by del theta along theta direction plus del v by del z along z direction, or z cap or k cap. Similarly, when you write for spherical coordinate system, so gradient of potential equals to del v by del r along r direction plus 1 by r del v by del theta along theta direction plus 1 by r sine theta del v by del phi along phi direction. Okay. So ultimately, what point I can conclude? The relation between electric field and electric potential equals to E equals to minus gradient of potential. So if you know the potential, if you take the gradient, you'll get the value of electric field. Okay, so this is one-to-one relationship between electric field and electric potential. So to solve the problem in electric field theory and associated numerical problem, you require to know the very basic of electric field and electric potential. Okay, so if possible, in my next class I'll discuss what is curl, what is divergent, and what is del operator, and how they are useful to solve the problem in field theory. Thank you very much.